with this algorithm? Can anyone see it? Yep.
Like maybe the distance that we measure to update the algorithm, we could basically like sum over all of the distances that we didn't get correct. Like we didn't get the correct prediction, and we just sum all of those predictions into one function, and try to make it as low as possible.
Suppose we were to interpret this as stochastic gradient descent. What is the loss function of a single example, single training example? Yeah.
It's just 0 or 1.
0 or 1?
Like if it's misclassified, or if one example is misclassified, then it's 1. If it's not,
If you do that, the gradient update, the derivative of 0 or 1 is not is flat. So it can't be that, because that's the update.
Probably the distance. So we have this line that separates right now, and we have that that point that we try to classify, and we did it wrong, for example, and that distance, I think, would be the loss function.
Okay, that's actually very close to the right answer. So this is the loss function. The loss function for a single training example, and again, using the SGD principle, everything decomposes adequately to its constituent training examples, is the maximum of 0, so it's basically the negative this sign distance. I'll normalize it, so this is the negative unnormalized sign distance multiplied by the label, and we're going to floor it at 0. So what does that mean? That means if the sign of our scoring function agrees with the label, then this is going to be positive, and we'll have classified it correctly. In which case, the negative of that is going to be negative, but we maximize it at 0, right? So if we score the model, if our score agrees with if the sign of our score agrees with the label sign of the label, we're in this regime, which is flat, so the gradient is 0, so we make no update. If the sign of our scoring function disagrees with the sign of the label, then by this formula we're in this regime, and the slope of this is linear in the feature value. So we make an update in the feature value. So implicitly, when Perceptron is up, so you can actually interpret the Perceptron algorithm as implicitly doing stochastic gradient descent with this loss function and a step size of 1. Don't actually need this for anything, for the homework or anything. This is just so you can sort of try to understand and take a more global view of how these different methods are connected together mathematically. Any questions? Yeah.
So you said that stochastic gradient can be parallelized, right?
Yes.
How do you make the updates when you parallelize?
That is an active research area, actually. So people have some ideas, and people are still thinking of better ideas. The main issue is that you don't want to overwrite the updates, right? That's one thing that people deal with all the time in distributed systems. And that's just something that's an issue in distributed gradient descent as well. I can point you to some resources of sort of results that people have. I don't really want to get into it right now. It's going to be a long and involved answer. But there are tricks you can do to maintain consistency. Yeah?
Could you explain a bit how the stochastic gradient descent is improving, I guess, computational speed over the non-stochastic gradient descent?
So there's two things at play here. One is that you don't have to imagine, let's just think of a thought experiment. Imagine we had 1 trillion data points. Our data set was 1 trillion, right? It's like a few petabytes. It will take you an hour to do one gradient update. And then your step size is something really small. It could very well be the case that if I just look at 20 examples and I do a gradient update, I'm already making progress. I mean, so the advantages become really stark when the training sets become really huge. Right? If you have a small training set, like 5,000 examples, it doesn't matter. Literally does not matter. In fact, gradient descent is probably faster because you can vectorize 5,000 training examples in a vectorized operation. So it's like optimized. But if you had, 100 million training examples, it matters. Okay, so just to recap, we started with this, at the end of last lecture, we started with this pipeline, right? Training data, model class, choose a loss function, cross-validation model selection, minimizes the objective function, and then we have a good model. By and large, the only thing that we added to this picture for this lecture is, how do we actually solve this optimization problem, right? Which is, of course, very important. And in the next lectures, we'll be talking a little bit more about expanding on this concept, and a little bit on this concept as well, right? Not just binary classification, not just linear model classes, and different types of loss functions that we can choose. So for next week, different loss functions, nonlinear model classes, regularization, and recitation tonight.